That ended in 2004, and that's when Kim went to Georgia Tech as an assistant professor. She's been there since. Many successes, true to our theme, true to our other speakers that we've heard. Kim was awarded a career grant. She was selected for the PCASE award. And one of the, a little bit less of a grand award, but I think just as important and that really plays into her success is undergrad mentorship award. And something that, in addition to the research we're going to hear about, which involves tropical climate in the Pacific over a very important time scale, one of the things that I really want to reach out to our current students on this, because we have all graduate students here. Kim has had a lot of interaction with undergraduates, and one of the things that she's done for about 10 or 11 years is challenge those students to come up with ways to reduce their carbon footprint in relationship to our research on how our increased carbon footprint has been changing the climate over this very important time scale that she was telling us about. And I just asked her before the talk, how many pounds of carbon has your program been able to save? She estimates between 20 and 25 million pounds of carbon. Now, of course, we emit a lot of carbon, right? So even though that's in millions of pounds of carbon, it might not be that big, but still, it's a very impactful way to play research into teaching. And I know with our students this year, when we got to evaluate all of the fellowship obligations, I don't think there's a single one that didn't talk about being impactful in communicating science. And that's one of the ways I think that Kim has been very successful in taking her research and putting it into play and having an impact in our world. I really look forward to it. I hope that you're excited as I am to hear about Kim's research and how this interplay has worked out for the group.
Great.
I'll hand it to you.
All right. Thank you. Thanks, Brad. All right. Well, thanks. Live? Okay, good. Thanks for that introduction, Brad. And it has been actually an absolute amazing opportunity to come down here for the first time. I've never been here. And meet all the people from the USGS, where I was able to spend some time this morning, to all the students and the incredible lab facilities that you have here. Participated in the Science Cafe last night. I didn't get to see the Dolly Museum yet, but I'll have to come back again. So plenty to chew on for a next visit. So thanks for your hospitality and thanks for the opportunity to share some of my work with you today. And I'm not going to go further than the title slide before I acknowledge some very important contributors, and those are my graduate students and undergraduate students who are listed there from Georgia Tech over really an arc of probably 15 years of sustained work in the coral world, coral side of my lab's house. And then also I've had sustained funding from National Science Foundation over this time period, and a smattering of NOAA money even. So yeah, very grateful to that funding. And we talked, I know Dan Rudnick talked a little bit about El Niños yesterday and the California's obsession with them, but El Niños are a global climate phenomenon and they pack a punch. And this is just showing you a map of the coral bleaching and mortality that took place across the last El Nino event as compiled by Terry Hughes in a landmark paper just a couple months ago. So I encourage you to go check that out to really digest the broader context for some of what I'm going to talk about today with regard to our reconstruction work. So El Niños are bad, but La Niñas are also bad, right? So we tend to get really excited about El Niños as physical scientists, but La Niñas are rarely devastating. And of course, this is an unforgettable image from 2017, record-breaking hurricane season. It needs no introduction here in Florida. And of course, this is a kind of a glib portrayal of this last El Nino event and its relative magnitude. It was called the Godzilla El Nino. We were worried it was going to really be the largest ever. It may not have made it quite to that level by a variety of metrics, but by some metrics, it was the largest on record. And the metric that I care about in my site, it was the largest El Nino event on record. And so this is something that really came on top, as Dan Rudnick told us as well, came on top of a year of sustained warming before that and really led to a very pronounced and prolonged period of warming across all the tropical oceans that obviously had some contribution to California and Florida as well. And so this is a record of El Niños going back for the instrumental record to 1880, where you should not trust anything you see there. But you can see the last big El Nino events took place in the last several decades of this record. And I put the red dots on those with their relative magnitudes. It's kind of hard to see where they land. But central tropical Pacific temperatures warm close to 3 degrees. That's the El Nino side of this plot. And the bottom is La Nina's. You know, these 4 very, very large events. So we had the 2015-16 event. And prior to that, we had the 1997-1998 event, which was also devastating in global impact. But of course, you know, from my perspective and the perspective of many people in this room, this plot would look more like this in reality, where we have a dimmer and fuzzier picture of instrumental records of temperature in the deep tropical Pacific, where this phenomenon is born. You know, basically prior to 1950, you're down to a very limited subset of data, and kind of every decade you lose more and more till 1900. You're really gazing through very foggy lenses to try to understand the frequency and magnitude of these events. So really, our whole record is contained within the very late 20th century in the most robust form, and before that, we really have to rely on some of these reconstructions to understand what's going on. So if we want to answer this very seminal question in climate science, one of the most pressing questions in climate science, a source of natural extremes, whether that is getting stronger with climate change or changing in any way, really, we would really like to know about it given its impacts. So we can wait 100 or more years until we have enough statistics piled up to tell you whether this event is changing in amplitude or frequency. We just need, that's how many events it's probably going to take before we can say definitively with the instrumental record. Now, I am a patient person, but I am not that patient, and I know you aren't either. So the only other option that we have as a community of scientists and stakeholders is to turn to the paleo record, turn to these records that predate the instrumental era and help us understand the magnitudes and frequency of these extremes going back really as far as we can, but of most relevance would be the period that would extend directly from the instrumental record, like several centuries, millennia. That would be a really relevant baseline to compare with recent trends. So that's what we're going to do today. We're going to bring you up to date with what I've been chewing on for 20 years now. I started working at a series of sites called the Northern Line Islands back in 1997. And this is depicting Palmyra Atoll, where I first started working for my graduate thesis. And then I started working on Fanning and Tabuaran and Christmas Island since. And we've been going there several times a year in some cases, but at least once a year through this whole period as a lab group in trying to build as much as we can in terms of the paleo reconstruction, make it more robust, make it longer, make it better, understands its strengths and limitations. It has been a 2-decade-long obsession, absolutely. And you can see why, right? These places are amazing. They are remote. This is a picture of Palmyra, which is a research station right now. If you ever have a chance to go. Don't miss that opportunity. These are incredible, inspiring places. And as a baby graduate student, I realized that if I could find any way to get back here on a regular basis, ideally not on my own dime, I was going to be doing that. So this is another picture from Palmyra above water. This is another picture of one of the islands. With these kinds of images rattling through my head, I've really built a passion and a dedication to these places that is kind of woven into my soul, you might say, right? When we have these research sites that are iconic parts of our being and our life stories. This is me drilling underwater. So this is the reefs that are accreting there are very remote. They tend to be very pristine, whatever you call that, when nothing on our planet can escape the ravages of global warming and ocean acidification. But relative to other reefs that have really strong human impacts, these are fairly remote and pristine. So this is a hydraulic drill here that we're using to extract this coral core, and I know that the USGS folks over there showed me bins and bins and bins and bins of this, so I know you guys know what these things generally look like. You know what we can do to employ geochemical techniques to reconstruct back in time, which is what I'm going to talk to you about today. And so we've been collecting these things since 1997, cores from these remote sites. And it's not only the modern reef that we use for climate reconstruction over the last 100 or so years. The corals that are growing on the reef now, you can't go to a coral that's growing right now and expect it to give you a core from 1,000 years ago. So we have to turn to these fossil coral archives, which in this case, you can see this big boulder lying on the beach there. This is a photo from Fanning Island, and this is the kind of material that we turn to that predates what's growing on the modern reef today. So this material can be up to 7,000 years old, some of it that we've collected is, and we have to use uranium-thorium dating techniques to understand when in time these samples grew. Because this big, old, ugly fossil coral will look exactly the same as one that is 50 years old and 5,000 years old. They all look the same to me. I wish I had mass spec eyes. But we have to drill everything and collect everything on site and then ship it all back to Georgia Tech and go through rounds and rounds and rounds of dating to figure out which of this material we would like to work with for high-resolution geochemical paleoclimate records. And so people always ask me how these things get there. Like, this is a huge boulder. This is 2 meters in diameter. And how did it get there? And I wasn't there when it happened. Probably wouldn't want to be there when it happened. But obviously, some very large wave activity rolled these things onto these beaches. They're all on ocean-facing beaches on most cases, the leeward side, where we have these really healthy reefs grown up. And we have these scattered across these beaches. We can use them. So here's a cross-section of a coral core that tells you how quickly these things are growing. So they're accreting year by year. And you can drill a transect down through this material that's going to give you samples that you can analyze year by year. And the chemistry that we use in my lab is based on the oxygen isotopic composition of the coral skeleton. And so the coral skeleton is comprised of calcium and carbonate. And so the isotopic signature that we're looking for is contained in the carbonate as the ratio of oxygen 18 to oxygen 16, which is very, very sensitive to changes in ocean temperature. And this is a thermodynamic effect that you can reproduce in a lab. It's very well established over 70 years of seminal work. And then it's also influenced, of course, by the starting material, the seawater that the coral uses to accrete the skeleton. So that is kind of a dual influence on this potential, this proxy of interest. And so I have a star here after the delta 18 of seawater here, because this is a variable that very closely tracks salinity in the modern ocean. And we know that because we've gone out and we've collected samples. This is a paper out of my lab. I've been doing a lot of work on this to try to understand the relationship between oxygen isotopes and seawater. And I wanted to note that we have a new US CLIVAR working group on water isotopes in the climate system. So if anybody's obsessed with water isotopes like me, get in touch. We're starting this 3-year working group to try to dig into this kind of glib statement a little bit more in nuanced fashion and see what we can do with a novel ocean tracer like this. So this is a very potent tool. And we generate powders at monthly resolution, so then we get monthly resolved records out and we can talk about extremes like El Niños. And we take these powders and we take them to the mass spec room, and when the mass spec is working, which is roughly, varies significantly year to year, let's say, it looks like this. So we have a day glow light in the back of the mass spec, and it's, we really don't have a day glow light in the back of the mass spec now. But this is a really, real life lab because we have duct tape on the liquid nitrogen line here. So this is not staged, this is actually my machine. And this is my graduate student, Hussein, and we have a computer facing away from us, which is what we all do, how we like to work. And this is, this is one of those calm shots that they do. You look back on it like, what? Why did I let that happen anyway? We try to keep this machine running. This is how we measure the oxygen isotopes on the coral skeletons. And we measure, we're able to measure one sample every 35 to 40 minutes. So when you're talking about thousands and thousands and thousands of data points I'm going to show you today, 40,000 measurements I've made for the work I'm going to show you today, you're talking about years and years and years of work. So how does this proxy work in the region that we're using with the carbonate system that we're working with? So this is how it works during El Niño events. So this is a map of the Pacific, and here's the Central Pacific island chain that I've been working on. And this is a map of sea surface temperature anomalies during February 2016, during that really large El Niño event. You can see it's obviously very warm at my research sites. And this drives a change in atmospheric circulation whereby it gets relatively rainy over this warm water in the Central Pacific. So this is outgoing long-wave radiation, showing you this kind of cloudy, rainy conditions over my sites, and of course, canonical dry conditions across the Western Pacific. And so with respect to the carbonate oxygen isotopic proxy that we're using, this works really, really well for us. Okay, I have to say I didn't really fully think this through when I started working here, but I'm really happy it ended up working out this way, and it's really why we have such a great signal of El Nino in our records, because during El Nino events, it gets warm, and that drives the coral delta 18 values down relative to normal conditions. And then when it gets rainy, this also drives the coral oxygen isotopic signals down. And so we have a compound signal at our site that is really useful for amplifying the signal to noise ratio with respect to most proxies that you might pick up and try to do this with. So we're very lucky with this specific target of interest, which is El Nino, at this location with this specific proxy in play. That's why we do so well. So when I show you the records I'm going to show you, you'd be like, I don't believe that she's faking that data. It's because we do so well, because we are using the right proxy in the right place for the right purpose. And here's those data. So this is a calibration over the last 40 years or so. We've drilled dozens of corals from the modern reef for calibration. I'm showing 8 of them here, run at monthly resolution. And so you can see them in colors, and then you kind of can't see in gray the OISST instrumental data set, it's only available via satellite era, of course. And so here in gray, kind of covered up by all these corals, showing you the warm El Niños and the relatively cool La Niñas, and the fact that these corals are all telling us basically the same story about the recent history of temperature at this location. And they're basically telling us the same story across the set of corals that we have brought to bear on this calibration. So we have short corals and long corals. I have a work here I want to highlight over the 2015-2016 event that an undergrad in my lab did. And we have now 14 corals analyzed over that interval. And so I'm really looking forward to getting that out to the community and talking about what a big El Nino looks like at some of these sites in the record, the rock record. And this is, of course, really attributable to whole generations of people that have gone through my lab, but also kicked off with Mike Evans' work with Rick Fairbanks at Lamont back in the day when they first drilled the first core at Christmas and worked it up for El Nino reconstruction, also plotted here. So obviously, the name of this game is replication, replication, replication. Aside from location, 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 it's really hopefully demonstrating to you the benefit of going after this kind of plot, right? You learn a lot more when you generate a plot like this than if you'd stopped at 2 or 3 corals, right? And so the streaming people can tell you this, the physical oceanographers tell you this. This is something that we as a payload community can really strive for and take ourselves and our work to the next generation. And so this is what this looks like on a 1,000-year time scale when you combine those modern records, which are now just a tiny sliver of the last 40 years of this last millennium plot. And these are uranium thorium dated fossil corals from Christmas Island, all run at monthly resolution. And the red is just indicating the mean of that sequence running through the high resolution data. And so up is warmer and wetter, and down is cooler and drier, just for reference. And you can see the unprecedented levels of oxygen isotopes that were achieved at this site during the 2015-2016 El Nino event with respect to the data that we have available. So there's a lot of information packed in records like this, including the fact that, yes, it's getting warmer, which is not really a newsflash per se. But what we really like to know about is about the nature of the variability as it's changed over this time period. So if we look at these high peaks, these are El Niños, these troughs are La Niñas. How can we wrap our arms around measuring the variability in these sequences and tracking that through time and seeing if there's been a change from pre-industrial to present? That's a lot of data that I need to get on a plot. And so I showed you it just was Christmas just before, but now I'm going to show you data from 3 different islands, so Palmyra, Fanning, and Christmas Island, over 20 different expeditions, 20 tons of coral shipped back to Georgia Tech over the years. You can imagine the excess baggage charges on that. The amount of radiocarbon dates, you can imagine that bill, let that think in a minute. The amount of uranium thorium dates, yeah, this is just money, 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 time, time, time. This is over 2 decades of, an obsession and many, many theses and many, many work. We have over 2,000 years of data compiled over the last 7,000 years that I'm going to show you, which is pretty good coverage, right? And it's all monthly resolution. So I'm quite proud of achieving that basket of data density over the last 7,000 years. Obviously, it's not continuous. It's not 7,000 years over the 7,000 years. But it's going to tell us a lot of information. We've had over 20 students involved from undergraduate to postdoctoral scholars. And of course, I bore 4 kids during this period, one of whom is sitting in the front row, and I lost 0 husbands. So, I am winning. I am winning. So if we turn to what we learned from this grab bag of data that we've been working on so fastidiously over 7,000 years, now I'm not going to show you the raw sequences, which are just going to look very squished in a small little peak trough narrowed stream of data in 7,000 years. Rather, I'm going to use a metric that's going to measure the interannual variability in the sequence and plot it on a y-axis where up is going to be higher variability data and down is going to be lower variability data over 7,000 years. This is a very complicated plot. This is like 2 decades of my life and many lives of my students plotted on one plot. So just, take that up for a minute. Take it in. I'm going to explain it, and then we can talk about what it means, what it doesn't mean. So this is work that's been compiled by my recent PhD student, Pam Groth, who's now at Mary Washington as assistant professor, and it's under review currently. And so what we have is 0 to 7,000 years ago, and on the y-axis we have the change in the standard deviation of ENSO as measured on these monthly sequences. So we literally just take a 2 to 7 year, for the geeks in the audience, you take a 2 to 7 year bandpass on the raw data, and we take the standard deviation and basically these choral snippets, and we plot that. And then the error bars on here are not really error bars, it's just indicating the range of ENSO strength that's encompassed in a given record. So it's trying to reflect the fact that over a single 100-year record, there are 20-year intervals that are really high in variance and 20-year intervals that are very low, right? So I'm trying to tell you what the richness of that individual sequence is. Each one of these is a choral record from different island, and they've all been uranium thorium dated. And so you can see going back in time here, we have very little coverage, relatively little, but that this looks very similar in spread and kind of where the data land to the last millennium data. And there's this indication of significantly reduced variability in the middle part. And then if we come over to the modern corals, here are all the modern corals we've recovered from the 3 different islands. And so we have Palmyra, Fanning, and Christmas. And these error bars are reflecting the range of full 20th century variability, where you have some really strong decades in the 20th century with respect to El Nino. This would be the last decades. And then relatively weaker variability. And this benchmark here that we've chosen for 0, about which we measure El Nino strength, is relative to the 1987 to 2007 ENSO variance period. So it's basically what we have lived through in the recent past is our benchmark. It's a totally arbitrary benchmark. We could have chosen any benchmark, but we think it's a useful one because we've lived through it. And we have really good data from our lab to really pin that down, as I showed you on that calibration chart. So again, just for the paleo geeks in the room, to note that there's this really long interval, protracted interval. So Pam's whole thesis was mostly concentrated right here, trying to find if we could get any sequences that are falling up in this range, and we failed. All of her sequences that she generated, over 25 of them, are falling down in this range of low ENSO variance. And this is very contrary to the paradigm that's out there about the history of Holocene ENSO variance. I'm not going to go into that today because I have other stuff I want to talk about, but I'm happy to take it in questions. It's very interesting what it means about the dynamics of the system and what it responds to and doesn't respond to. But the main thing I'm going to talk about today is the primary observation that most of these fossil coral data are falling below this late 20th century benchmark. You can see it by eye. It's not unprecedented. There are some periods in these sequences in the last millennium which do have slightly higher ENSO variance, but these are little 20-year windows. And so most of these are falling way under. And so obviously we would like to ask the question whether there is a statistically significant change from the pre-industrial to the late 20th century data, or whether this is just a chance sampling of a system that's really all over the place and we just don't have enough data to fully flesh out the range of variability. And so that's a really hard question to address because we don't know what a stationary system of El Nino looks like. We don't have a long record sitting out there to say, this is what El Nino does for 10,000 years, and you can measure how high it gets and how low it gets and for how long it gets parked there. We don't have such a thing, that it doesn't exist. So what we have to use as a null are model outputs. So we take model outputs from CCSM4 and the GFDL 2.1. We take a linear inverse model of El Nino statistics that Antonetta Capotandi gave us. This is, again, for the nerds in the room who are interested in this setup. But these are thousands of years of realizations of ENSO in basically control simulations. And it goes all over the place. It's amazing what El Nino can do in these climate models if you just push go and you wait long enough, right? And so what we did is we tested whether this coral data as a whole set is consistent with statistics of those control simulations, or whether it implies a non-stationary change in ENSO statistics. And so that's really where we're going to go with this. And so this is a test that we applied statistically, testing against a stationary null, right? That's the null hypothesis, is a stationary data set. And what we found is that the observed difference from pre-industrial to present is much, much, much higher than can be backed out of these null hypotheses by chance sampling of a highly variable system. Okay. And it's not just a little bit, it's actually quite a bit. So we are above the 99% significance threshold. Now, there may be really important challenges with these nulls. They're not perfect. It's what we have. It's the best that the climate community can offer us right now in terms of understanding long-term ENSO variability. However, it seems from our data set that it's virtually certain, with the testing that we have provided, that 20th century El Niños are significantly stronger than pre-industrial El Niños. And so there's a lot of fine print here that I don't know if you can read that, but there's some caveats to that. Okay. However, it has been a very important period for paleo-ENSO work. We have had a number of seminal studies published over the last 5 years that really show us similar results. These are different data sets from different regions of the Pacific that all come to the same conclusion, which is that there's something about late 20th century internal variability in the Pacific that is statistically different than the internal variability from the pre-industrial era. Some of these records are only several hundred years long, some of them are longer. But this is taken together, a body that would seem to imply that there's been a shift in ENSO properties that has already emerged in the modern day climate system. And of course, the implications would continue. So that's very interesting. And I think that really opens up a whole new set of questions for climate science to chase down. So I'd love for modelers and dynamicists to think about what they could do to help us understand what about El Nino has changed. Is something about the amplitude implied from these records. And I want to make clear that all of these records as a whole, including my own, combine aspects of temperature and they combine aspects of hydrology, right? So I just told you one of the strengths of my sites is that we capture that hydrological component of El Nino to increase our signal to noise. And all of these records to some extent are incorporating some hydrological response to El Nino. So it's quite possible that what we're seeing is an amplification of the hydrological response to El Nino, which is something actually that models seem to suggest may be happening with greenhouse gases, and that this is basically written out into these hydrologically sensitive set of paleoproxies, that we're already seeing that. So that's one kind of Occam's razor approach, combining some model output. But I want to get back to something else, which is important in terms of how scientists approach their work, the context that they work in recognizing that we don't work in a vacuum, and that it's important to ask yourselves when you're going to do something different with your life. And this event was a bellwether event for my research site and also for me personally. I wanted to share some of that with you today. So take us to 2015 in November. This El Nino event is ramping up. And what it would do to my island chain here in Northern 9 Islands was subject it to over 9 very, very long months of bleaching level stress for the coral reefs that I've been working on. So, here's a scientist who spent her whole life chasing El Ninos and coral records from these sites, and this massive El Nino event is underway. So I wrote to NSF and I said, please give us some money. We want to go down and measure this thing, all the time. We want to instrument the whole reef. We want to go down there every 3 months to service this array and take all these samples, all the geochemistry, all the isotopes. We want to take pictures and samples of the reef to understand what's going on. They said, that sounds like a crazy idea, but okay, which is really great. Sometimes that works out at NSF. And so we were going down. So we had this huge temperature stress translate into this bleaching event. And so here's me installing a CTD. Thankfully, didn't lose a CTD on that expedition because it's crazy down there at 30 feet. This is 30 feet measuring temperature and conductivity and, well, depth is pretty boring here. In August 2014, and you can see this site is incredible. We have near 100% coral cover. In November 2015, this was 5 months of bleaching stress that the island had experienced. Most of the reef at this exact same site was bleached, 30 to 90% bleaching. We'd already lost some of the most sensitive species around the island to bleaching and death. And we went back in April 2016 for one of our final expeditions, and basically the reef was dead. It was just dead. 85% of the reef died between November and April over those 6 short months, and it was still over 1 degree C warmer than normal in April 2016. So when we left, we knew more corals would die when we took that plane out, right? And words cannot describe the feeling of jumping in the water as a scientist, having waited for this event your entire life, and then looking at your reef and saying, like, how do you reconcile intellectually what you knew you would be facing, right? Because you watched your monitor, you watched the temperatures, right? With seeing a scene like this and knowing what it means for this reef never looking the same that the reef that you dove on. That's pretty impactful experience. I was not ready for it, but you're there and you're on a mission and you're doing your work and you have safety issues and you're spending NSF money and you need to get the job done. So we did an amazing job. We had an amazing set of expeditions. It did land me, most unfortunately, on the front page of the New York Times on April 9th, 2016, really talking about that experience, being one of the primary witnesses to what would become the largest global scale bleaching and mortality event in recorded history. Crazy. And then, I went down in November 2016, and I was on the island when something happened back home here that shocked me even more to my core, right? Like, literally talking about 6 months later, from having that April experience to having Trump get elected. And so I had to deal with that on an expedition again. It was a double whammy, right? As a climate scientist, as somebody who'd just seen what she had seen as a mother, it was shocking to my core. And I came back several weeks later and everybody was like walking around, like doing stuff. I'm like, what the hell, people? Like, it's just like, can't we have like months of collective mourning? And everybody was just like, oh yeah, it kind of sucks. Let's hope for the best. Like, oh, it won't be so bad. And so like, I took my 2 months in bed. Honestly, I was just like, ugh, y'all, like, no. And so I was very, very shattered to my core, thinking that maybe there was a way with another president forward, and then the crush and wave of recognition that the future that I may have dimly hoped for maybe wouldn't come to be. The threat was much larger than I had ever thought possible, and I can't not be changed by 2016, pretty much forever. And so this is something I came to in 2 months of kind of lying around in bed, is that we have an opportunity to demonstrate the resilience under extreme and acute stress as a society, frankly. Certainly as an individual, right? But more largely as a society. And so, I have some ecologists in the room, right? Right? Yeah, you have disturbance, then you have recovery. It can take many different shapes. We study it, we try to learn from it. And we probably can learn some lessons from ecology actually in this. But this is why I ended up getting out of bed in the morning. And one of the first things I did in this new wave of fumbling was participate in a Stand Up for Science march at AGU on December 15, 2016. I'm still like, lost. Like, I've lost the plot for real, but like I appeared there, I kind of look lost. Like, I'm like, what am I doing here? What am I going to say? So I got this call like the night before. They're like, we'd like you to say some stuff. Like, somebody more famous dropped out. And like, you're going to maybe... And I was like, oh my God, sure. And so I'm like, what am I going to say? When I didn't prepare anything. I don't know what this is. I don't even know if I'm going to do it. I may chicken out. Like, I have no idea. And so I said some stuff. I opened my mouth and stuff came out about coral reefs, about climate change, about how it felt to see that, how it felt to have him elected when I was down there, and just trying to bring some words to what I was feeling inside, which is that we have not done our jobs. I had not done my job, and our community had not done its job. And I know there are many, many reasons why. We can talk forever about why it happened and how it wasn't our fault. But my perspective is we have to make a change. We have to turn the page. And so this is where I began to find my way on January 21st, 2017, in DC with my daughter. And I realized that surrounded by millions of people, that I was not alone, right? That there were many, many, many people standing in DC saying, no, we are drawing a line and we are not going to let this happen. It's not going to go down on our watch. So this is me marching with a group of scientists called 500 Women Scientists, and I've found great nourishment and purpose in their activities. There probably is a pod somewhere here. Yeah, you're nodding, good. I'm on their advisory board. I lead the Atlanta pod, and I started a high school pod at our local public high school. So it's great, look them up. They are purposefully intersectional, unabashedly feminist, and they care deeply about science and data. So this is me also taking a big step, signing a collective letter, my first of many dozens of public letters I signed to the administration, checking them on their facts related to science. I'm not going to read you that, but it was very scary to sign this in early 2017. But I have since realized you don't die. I signed it, it went out, I circled on the press. I'm like, coward in my office, like, oh my God, they're going to find me. And you know what? Nothing happened. It was amazing. I just got to be part of something. And this is me on January 1st, 2017. It was my twin's birthday, which is a big deal for me, obviously. And I woke up and I said, I bike to work twice a week, and I'm going to walk my kids to school twice a week. In 14 years of living in Atlanta, I had never biked to work once. I had never walked my kids to school once. Okay, so I started biking to work every day, and I have not looked back. It has changed my life. It has let me feel purpose and hope and community in new ways. I'm involved with my neighborhood traffic board, neighborhood board as their traffic chair, which is crazy. I mean, totally crazy. Way out there for me. It is like an other world when you go into that boardroom. It's really fun to learn about other perspectives, learn what other people care about. So it's been great to engage. Obviously, I'm all for biking and bike infrastructure. I'm really trying to move the needle in my very unbike-friendly neighborhood. The other thing I very much care about in this world is recognizing who we've left behind and who's not at the table and who's not going to help us towards a sustainable world if we don't ensure it's a just world as well. And so for this, we need all hands on deck. So I wear things on my sleeve I've never worn before. This is my house. So you drive by my house, you're like, wow, who lives there? I live there, and I am very proud of wearing these things on my sleeve. And aside from my formal role as a champion for diversity, equity, and inclusion at Georgia Tech, I appear at public events, and I speak as a scientist, as a mother, as a champion for equity. And this was me at the March for Science, having a really great time in Atlanta. I do have a Twitter profile that I use and misuse quite frequently, so you can check that out. I have a lot of fun, all trial and error, all pretty terrifying. But I wanted to end on a positive note, and something that I think really flags the key role for higher ed in solution spaces. We have institutions that don't ask themselves enough about what they could be doing to create a more just, sustainable world, right? We're living in like a 50s model. I don't know what model we're living in, but we need to turn the page and ask ourselves what we could be doing more and challenging our institutions, challenging ourselves to challenge our institutions. This is something Brad talked about. I spoke about it last night. This is the cumulative carbon reductions from 2007 when I first started this as a class project, ramping up to last semester where we achieved 12 million pounds of carbon dioxide reductions from undergraduates. who have busy lives. They run track. They have a research project in engineering. They have a sick parent. I mean, they have full lives. This is like probably, honestly, less than an hour or two of their week, right, over 3 months. 30 students, 3 months, not even a part-time job for them. This is what they've achieved. So it is actually amazing. We're saving carbon, we're saving money, we're empowering and equipping these students. And I talked about the SunTrust team last night at the Science Cafe, changing the default car rental across the entire company from intermediate to economy size, $40,000 a year of savings to SunTrust, millions of pounds of carbon dioxide saved per year for all of us. Now, 12 million pounds is, you may say, I don't know, that sounds like a lot, I don't know. This is 12 million pounds, 34 homes fully powered by solar panels for 20 years. That's 12 million pounds of carbon dioxide equivalent. So here's some the free carbon literacy for you here. So please yourselves become carbon literate, start to understand these things and challenge yourselves. This is a new program at Georgia Tech that I'm very proud to lead, focused on solutions, focused on student solutions, more to the point. Y'all are our great hope, right? I mean, old people like me, maybe it'll change a little bit, but y'all are going to be able to shape yourselves into the champions that we need you to be. And this is what we aspire to do in the new program at Georgia Tech. I'm aided and abetted by our ex-president, Dr. Clough, who comes to me from the Smithsonian, all fired up about how we can save the world. So thanks to him, and I'm really grateful for Georgia Tech. And so I just wanted to close with a couple amazing photos from my various expeditions. Hope to demonstrate to you what you can do if you science with passion, which is definitely what I do. When you science with purpose, which is what I very much aspire to do. This is me making a total fool of myself on the Years of Living Dangerous episode 3, if you want to check that out, in Christmas Island. And science with love. So we have to find a way to help each other through this too. And we have to move our institutions and ourselves towards this just, sustainable future that we deserve and that our kids deserve. So thank you.